century. So there were these big, fabulously productive, exciting missions. You may have heard of many or perhaps even all of these, but they were so complex and so expensive that NASA got into a very difficult cycle in which the missions were so big, they cost a lot of money, that they couldn't take any risks. You can imagine if you're in charge of a multi-hundred million or even multi-billion-dollar mission, you're not rewarded for taking a risk with new technology. Rather, you're rewarded for getting the results. And so the best thing to do is use the same technology that the mission before you used. And so these projects got into cycles of using older and older technology. And they became so expensive that they were becoming less and less frequent, which made them still more important that they not fail, which made them still more expensive. And so they took even longer to do. There were even fewer missions. And this really fed on itself until it developed into a real problem, which I summarize here as the old way of doing business. As it says, before the discovery of eruptions, lava had to be carried down the volcano and thrown on sleeping villagers. This was expensive and time-consuming. And that illustrates how interplanetary missions were being done as the end of the 20th century approached. And so, as Glenn already alluded to, with some colleagues, I helped develop a new program called the New Millennium Program, the objective of which was test some of these high-risk advanced technologies on operational low-cost missions in order to reduce the cost and risk for subsequent missions. The idea was that New Millennium missions would take the risk so that subsequent missions wouldn't have to, and that would allow us to conduct follow-on missions, dedicated science missions, less expensively and more frequently. So that's the genesis of the New Millennium Program. And when we started it, we asked, what are these high-risk advanced technologies? If there were other good technologies that weren't high risk and that weren't especially advanced, then there was no need to test them on these operational missions. So we were focused on those. So what are the technologies that we need? Well, the first question that we felt needed to be answered was, how can we travel around the solar system more easily and less expensively? That's a problem that faces many, many missions, many, many projects. And there are many destinations that are essentially inaccessible and many missions that are truly impossible with the propulsion technologies that we had at our disposal in the late 20th century. And so let me just remind you of just at the high level how conventional chemical propulsion works. And to illustrate it, I decided to use an Apollo spacecraft in honor of Roger Chaffee, the eponym for Roger That. But this applies to all propulsion systems. Essentially, all propulsion systems work on the same principle. I just wanted to use an Apollo spacecraft for fun to illustrate it. So you take a gas and you heat it up, or you put it under pressure and you push it out of a rocket nozzle, and the action of the gas going out of the nozzle causes a reaction that pushes the spacecraft in the other direction. Same thing happens if you let go of the open end of a balloon. The action of the gas going out of the balloon, the action of the air, I should say, going out of the balloon, causes a reaction that pushes the spacecraft, or pushes the balloon, sorry, in the other direction. And so that's how propulsion systems work. We had a novel way of doing this, which uses the same principle, action and reaction, but where we didn't heat the gas up or put it under pressure. Instead, we start, and can somebody, like Glenn, can you just nod if you can see my cursor? Okay, good, thank you. So we start with the gas xenon, which is like helium or neon, but heavier. and inject it into a chamber, which is about a foot across here. And then we bombard these xenon atoms with electrons. If there's anybody in this in the meeting today, maybe not, who's old enough to remember the 20th century, I don't know if any of you remember the 20th century, televisions in the 20th century had an electron beam that scanned across to make the screen light up. So for all of us who are old enough to remember that, that's how it worked. Well, here we have an electron beam that sort of does that. It hits the xenon atom, bounces off. So here's the electron bounce off, but it knocks off another electron. So that creates a positive charge on the xenon, which we call an ion. You don't have to remember the details of that. It doesn't make any difference. What counts is we have this little charged particle we call an ion. And once it's charged, it can feel the effect of a voltage. So we have these two metal grids here and here that are very close together, spaced by only about 10 times the thickness of your hair, or 20 times the thickness of my hair, and you put a big voltage between them, and they shoot the ions out at very high velocity, 10 times the velocity of conventional chemical propulsion, at 90,000 miles per hour. So the action of the ions going to the right causes a reaction that pushes the engine and thus the spacecraft to the left. And so because we shoot these ions out at such high velocity, this system, as I alluded to, has 10 times the efficiency of conventional chemical propulsion. So this would be like having your car get 300 miles per gallon. And that's what would allow us to undertake these more ambitious missions. But because this was such a different way of operating, such a different kind of propulsion system, it needed testing on one of these New Millennium missions. And this was the highest priority technology of the New Millennium program. And here's a photograph of one of these engines, excuse me, operating in a vacuum chamber at JPL, just a few miles from my house where I am now. And you can see it really does produce the cool blue glow that you may have seen in science fiction movies. So that was our highest priority technology. That answered the question of how can we travel around the solar system more easily and less expensively. But now our next question is, what do we call it? Now, there were many names that people advocated and names that had been around for quite some time. The most common one was just electric propulsion, which most people called EP. So if you said electric propulsion, it didn't mean a Toyota Prius or a Tesla car. It meant this kind of propulsion system. Another popular name for it was solar electric propulsion because we got our electricity from the sun as opposed to nuclear electric propulsion, which is another version of this technology. And so that was generally called SEP or sometimes SEP. Now, there was also a NASA technology program that is a program of funding technology development called the NASA SEP Technology Applications Readiness Program, NSTAR, that everybody called NSTAR. And so many people said we should call this system NSTAR. And some people called it, some technologists, people working on this, called it Xenon Ion Propulsion System, which most people called ZIPS. So all of these names were in common use among the field of people working on this. So the question was, what do we call it? Well, fortunately, since I was in charge and I got to decide, and so I turned to the most authoritative source I could think of, which was a Star Trek episode called Spock's Brain. And I won't take the time to give you the details of the episode, but in brief, aliens come to the Enterprise, steal Spock's brain, and other things happen. And in that episode, when the crew sees this alien ship there, the The always capable bridge crew, of course, gives their reports to Captain Kirk, and then Kirk walks over to Spock and says to him, "What do you read, Mr. Spock?" And Spock responds, "Configuration unidentified, ion propulsion, high velocity, though of a unique technology." Well, I thought that was pretty persuasive right there, but Kirk wasn't done, because he goes over to Scotty and says, "Well, Scotty?" And Scotty says, "It beats me, but isn't she a beauty?" Both of them being experienced with space travel, Kirk observes it's an interesting design, and Scotty says, "I've never seen anything like her. And ion propulsion at that. They could teach us a thing or two." Well, in my view, that was an adequate basis for calling this ion propulsion. And we call the system the ion propulsion system. And that was the formal, official, technical name in all of our documentation. That's how we referred to it in all means. And that's how we referred to it even on a subsequent mission I worked on that Glenn alluded to, the Dawn mission, which just happens to be depicted in my background here. But a big part of the basis upon which I chose this was I knew that for outreach purposes, and I'm very interested in outreach, we could connect with the general public using a term like ion propulsion because of Star Trek better than EP, SEP, N-STAR, ZIPS, any of these other names. But I don't want you to have the mistaken notion that the idea for ion propulsion came about in Star Trek. Now, in a short meeting like this, I don't have time to give you the entire history of ion propulsion, but I will mention that it actually does go back pretty far. And in fact, in 1906, Robert Goddard, the father of American rocketry, that photograph isn't from 1906, but in 1906, he actually wrote, excuse me, in his science and engineering scientific notebooks about a concept which is very much like ion propulsion. And there's a somewhat later diagram there from a patent application of his in the 19-teens. And Konstantin Tsiolkovsky, sometimes known as the father of cosmonautics or modern astronautics, who really did very important work, not as well known in the United States, but very well known in the space community, and of course in in Russia and the former Soviet Union. In 1911, actually published a paper on this, and I think he may even have been doing some experiments of his own on something akin to ion propulsion there. But it also has occurred elsewhere in science fiction. And maybe you recognize the Star Wars TIE fighter here that Darth Vader and the evil empire used against Luke Skywalker and the members of the Rebel Alliance. Well, in the Star Wars universe, TIE, T-I-E, stands for Twin Ion Engine, because that was one of the most futuristic, coolest, advanced technologies George Lucas could think of. And to me, one of the rewards of working on a project like this is getting to turn that science fiction into science fact. And here's that science fact. So this now is an artist concept of the first mission of the New Millennium program using its ion propulsion system. So now we had still another question. What do we call the mission? I know you already know the answer to that because it was in my title, and Glenn and I have both referred to it, but how did we come up with this name? Well, the New Millennium program was testing these technologies like ion propulsion and others that I'll mention briefly later on that needed their testing on these operational interplanetary missions, or as we say generally, missions to deep space. But we also decided that New Millennium could test some missions in Earth orbit. And so these were, what we ended up deciding was just for convenience, for internal nomenclature, while we were formulating the program, we'd have these deep space missions and Earth orbiting missions. But then I recognized that, gosh, deep space, there's a pretty good connection there. Oh, and I should say, normally these missions then would get other, more public names with stronger public appeal, like you can imagine calling something Perseverance instead of calling it Mars 2020. But I thought the name Deep Space was pretty good, so we ended up calling it Deep Space One because, of course, of the connection with Deep Space Nine. And we did have subsequent missions as well, Deep Space Two, etc. And so that was motivation to just keep our informal and unofficial name and make it official. And that's what the name of the project continued to be throughout. So that's how we got started. And then just want to give you a little bit of an overview of the mission. We had actually 12 technologies in total on this interplanetary mission. Once again, the ion propulsion was the most significant, the highest priority technology. But we had a number of other neat technologies too, in some cases where we gave the spacecraft some of its own smarts to allow it or give it the capability to make decisions on its own, independent from the ground. And then there's a photograph of the spacecraft as it was being built. It isn't complete there, especially it doesn't have its solar arrays, but that's the main part of the spacecraft compared to the size of a person there as it was being built. And then we got off to a very nice start with a launch in October 1998 from Cape Canaveral. And once we got into space, we flew the mission. And I wanted to show you, just because I think it's fun, this is my favorite picture of the spacecraft. So I worked with the spacecraft in the clean room day after day after day for many, many months, actually more than a year. But this is my favorite photograph, taken by the famous 200-inch telescope on Palomar Mountain, excuse me, about 3 weeks after launch, when Deep Space One was 9 times as far as the moon. And there's the spacecraft. And you probably know that when telescopes take pictures of astronomical objects, the telescope has to rotate in order to compensate for Earth's rotation, to keep the stars fixed on the film or the electronic detector. And that's why the stars have all nice symmetrical shapes. But during that exposure, Deep Space One had its own independent motion through the solar system. And so the shape there doesn't tell you anything about its shape, but rather shows you it's flying on its own. And I just really love this picture because it just reminds me that we, humankind, all of us, not just me, we have spacecraft out among the stars. And I think that's really neat. And I should also mention, at the time this picture was taken, DS1 was so far away, it was 4 million times fainter than you can see with your naked eye. For you amateur astronomers or even professionals, if you're here, as a visual magnitude 22.5. So pretty remarkable, even that we could get this picture. Even that vastly overexposed star in the lower left is more than 100 times fainter than you could see with your naked eye. Anyway, so we got the spacecraft off on a good start and flew it on its mission. It left the Earth and the Moon behind. Excuse me. And we had a very, very successful 11-month mission of testing out the ion propulsion, those autonomy, onboard intelligent experiments, and all of the others. It was a very successful, very productive mission. And we were able to determine that ion propulsion and these others were ready for subsequent use by other missions. But then at the end of the prime mission in September of 1999, we still had this healthy spacecraft out there in the solar system, even though we had finished our technology testing, wanted to make the best use of this resource that we could. So we proposed to NASA headquarters that we undertake a new mission, which they approved, and that was to fly to a comet. And we thought this would be an exciting, ambitious mission. And so we embarked on that. And unfortunately, just a couple of months after we started, we ran into trouble. A device on board the spacecraft that was critical truly critical for helping the spacecraft orient itself in the zero gravity of spaceflight failed. And so Deep Space One then couldn't control its orientation. And it seriously, I mean, it was such a bad failure that headquarters and others said we should just abandon the mission, let it rest on the laurels of its extremely successful primary mission, and just move on, because it would be impossible to salvage the spacecraft. Well, tell you probably can't tell in the little thumbnail video, but I'm actually wearing here one of my Deep Space One rescue shirts, because we decided we should rescue it. We should try to rescue it anyway. And we undertook what was later described as one of the most remarkable rescues in deep space exploration. And I'm not going to take the time here to tell you about it, but I'm going to put in a plug that if you're interested in learning more about this, if you want to take 16 minutes, I just gave a TED talk just a couple of months ago during the pandemic. So I had to do it here, my house, just with iPhone cameras so the TED people could edit them together. But anyway, I called it, "If it isn't impossible, it isn't worth trying." And if you're interested, take a look at that. If you want to know even more about, and that doesn't focus only on this rescue, but principally on the rescue. And if you'd like to know still more about it, you can find this video as well. That's between an hour and an hour and a half long. But the point is, we were successful. We got the spacecraft operating again, and we were able to undertake our mission to continue on to the comet. But then there was a new problem. And to explain it, I want to remind you or explain to you how spacecraft hold their orientation in space. Spacecraft don't have rigid, fixed orientations. They're in zero gravity, and they tend to sort of move around. And so we call this the attitude, the orientation of the spacecraft. And we shoot a little rocket propellant out of one side, and it makes the spacecraft rotate, and then shoot it out of the other, and it makes it rotate back the other way. And many spacecraft, not all, but many, including Deep Space One, Voyager, many others, this is how they control their orientation, which we call attitude. And that propellant that we shoot out in alternating sides, we only carried a small supply of that. It's called hydrazine, because we only had planned for an 11-month mission. But the mission then became much longer. And for technical reasons during the rescue, we expended a tremendous amount of this propellant. So much that by the end of the rescue, we didn't have enough to control the attitude anymore for the entire trip to the comet. Now, when we're thrusting with the ion engine was mounted on a gimbal, so we could actually change its orientation. And so by gimbaling the engine, that is, pointing it to in different directions, and there we go. By pointing it in different directions, we could get the spacecraft to do the same thing of tipping back and forth, and we could control how much it would tip and how quickly by the direction we pointed the ion engine. And so that allowed us, whenever we were thrusting, to save the use of this hydrazine. And that was critical to our being able to get to the comet. So as long as we're thrusting with the ion engine, we were in good shape and we could continue on to the comet. But now we had still another problem, and that is, excuse me, that for technical reasons, there are times in the mission where it's better not to thrust, to coast like all other spacecraft do. Most spacecraft coast most of the time, just like the Earth coasts around the sun and the moon coasts around the Earth. And Perseverance, which landed yesterday, coasted for 6.5 months to get from Earth to Mars. With ion propulsion, you thrust most of the time, but you don't want to thrust all the time. So then we had a problem, because we got onto a trajectory where it was optimal to coast the last 4 months to the comet, but we couldn't afford to do that because we needed to thrust in order to control the attitude. And so we thrust at a low level to allow attitude control, but minimal damage on the trajectory. But still, to cancel out the thrusting, we followed the sawtooth pattern. So we were thrusting at a low enough level that the spacecraft could tip its ion engine to control the attitude while perturbing the trajectory as little as possible. Well, that's like the Enterprise when it thrusts at impulse power, when it's going more slowly, not at warp power. And so I chose to call that thrusting at impulse power. And Deep Space One, we actually ended up doing it more than just that 4 months leading up to the comet. We spent a great deal of time thrusting at impulse power, which is terminology that everybody familiar with, or everybody who's very familiar anyway with Star Trek would recognize those terms. And that's what we called it on Deep Space One. Well, fortunately, that allowed us to get to the comet. And I don't know how well animations work in Zoom, but this is just illustrating that when we got there, we had to fly through the coma, which is the cloud of gas and dust surrounding the comet, at very high speed, excuse me, which presented a significant risk to the spacecraft because the coma, this cloud, has dust in it, and the impacts of these tiny particles could be so powerful that even one comparable to the head of a pin could impart as much energy to the spacecraft as a bowling ball does when it hits the pins. So this was a very risky undertaking. And in fact, there were myriad risks, and the encounter should not have been successful. And in fact, it did not go as expected. In contrast, it was incredibly successful. And talk more about this in both of those videos that I alluded to earlier. And this is a photograph of the nucleus of the comet that we got, which at the time was far and away the best view we ever had of the nucleus of a comet. And in fact, even was 3.5 times better than our own objective for imaging the comet. And when you look at it from different angles here, you can even see it's sort of bent at the neck there. And you may have seen other solar system objects that look like that. This was the first time we ever saw one of these. And while there are multiple possible explanations for it, the most likely is that early in the solar system history, 2 separate objects came together at low enough velocity that they would connect but not smash each other apart. And then you would get this sort of bent thing like that. And there's a farther out view where now the colors encode the density of dust around the nucleus to show you that there was this very strong jet of gas and dust coming off the nucleus. That's not where Deep Space One flew, which is probably why it was able to fly successfully through this cloud. From Earth, we wouldn't have any possibility of seeing anything of this resolution. But that is in large part why Deep Space One was successful in encountering the comet. Well, so after that, the mission concluded, but let me just give you an overview of Deep Space One's interplanetary adventure here. So here's the sun in the middle. The green is the orbit of Earth. This is where Earth was when we launched in 1998. And where the trajectory is dark, orange I chose here, is where we're just coasting, where it's this nice xenon blue color is where we were thrusting. And so we coast and thrust and coast and thrust. We even, along the way, flew by an asteroid, but then embarked on our plan to aim for the comet. But you can see we were coincidentally just coasting for a very brief time here, but ran into problems. Then we ended up coasting halfway around the sun when we didn't expect to. We had actually expected to resume thrusting right about here. We coasted halfway around the sun, managed to rescue the spacecraft. Took us a little longer to get the ion engine going again. Then we thrust for a very long time with just a short period here where we couldn't chose not to for technical reasons, till we finally coasted through our time where we were imaging the comet and making other measurements. The moment we finished that, we had to resume impulse power thrusting so that we could keep controlling the attitude, even just to return our data. And that was the mission. And at the end of the mission, we said farewell to the spacecraft and gathered the team together to sort of give it one last fond farewell. We looked up at the sky and gave a salute to DS-1, our favorite spacecraft. And so that was the end of a very successful mission, but not the end of the influence of Deep Space One, because there have been many, many beneficiaries of the technologies we tested, including, see in the lower right, Perseverance, and in fact, all other NASA Mars orbiters, landers, and rovers that were conducted after Deep Space One used some of the technologies we tested. Excuse me. You heard Glenn and I have both alluded to the Dawn mission, which is there up near the B and beneficiaries, and again is behind me here. It used ion propulsion again to undertake a mission, once again, that would have been not just difficult, but truly impossible without ion propulsion. And it's the only spacecraft ever, as you heard, to orbit 2 extraterrestrial destinations. And that to me is very much like the kind of thing you see in Star Trek, where you go to one planet, do whatever you're going to do, and then go to another and do what you're going to do there. Star Trek was usually at one planet, you beat somebody up or make out with them, then you go somewhere else and do whatever you're going to do there. That's not exactly what Dawn did, but again, it was thanks to its ion propulsion system that it was able to do this. And so I just want to come back once more to the connection between the ion propulsion and Star Trek. And later in that same episode of Spock's Brain, the bridge crew here, there's another shot from Spock's brain, excuse me, the bridge crew discusses the sophistication of the alien ship that they're observing. And Captain Kirk says, advanced ion propulsion is beyond even our capabilities. Well, thanks to Deep Space One, it's not beyond our capabilities now, but thanks to Star Trek, we call it ion propulsion. So I hope you enjoyed the presentation, and thank you very much for listening to me. If you have any questions, I'd be happy to address them. And if not, then you get a little free time this afternoon. And I can't hear you.
I'm going to see if I can unmute.
Now I can hear you, Tina.
Yeah, I'm going to see if I can unmute Glenn.
Okay, thank you.
Okay, there I am. I have my voice again.
Yeah, welcome back.
Brain, what is brain? Oh, thank you so much, Mark, for that wonderful presentation. Like I first heard, a similar talk a couple of years ago, and so that's what got me interested in having you return for the opportunity with Roger that, and I'm so glad that you were able to do that. I'm looking here at some of the questions that we have, and there's a couple from that we've got, but I'm just trying to check here if there's anyone else that might have questions. Okay, there is one from a Michael. It says, oh, when DS-1 was finished, did you blow it up or is it just still floating out there? That's a good question.
It is a good question.
Are you still monitoring it? Is it still providing science?
It is a good question. We don't blow up spacecraft, at least not intentionally. Now, I actually thought about having a little more fun animation with a Klingon ship coming in to blow it up, but and now I wish I had done that, but no, that's not what we did. In fact, so I told you about the limitation in the hydrazine and how little we had for controlling the orientation, the attitude control. If we hadn't used impulse power, it sounds like I've changed the topic, but I'm going to get to the answer. If we hadn't used impulse power, DS1, Deep Space One would have died long, long before we got to the comet. But even with the impulse power thrusting, we still had to use a little bit of hydrazine. There are technical reasons for this. I could explain them if people want, but I don't want to take too much time. We still had to use a little bit of hydrazine. And after we flew by the comet, we continued to operate the spacecraft for another 3 months or so and did other experiments with it, mostly, in fact, with the ion propulsion system, but with the others as well, operating the ion propulsion system in various warp power modes and other things that were even riskier than we had wanted to do before. But at the end of that, there was so little hydrazine left that there was no place else we could go. And we were on the verge of losing control of the spacecraft. And so we intentionally turned off its radio transmitter so that it wouldn't be a source of interference for NASA's deep space network. That is, these large antennas that we have around, we have some in Goldstone, California, some near Madrid, Spain, and some near Canberra, Australia. And those are the antennas that we use to communicate with all interplanetary spacecraft, all of NASA's interplanetary spacecraft. We didn't want a radio transmitter out there that was a source of interference. So it was a fair amount of effort to force the transmitter off and ensure it wouldn't come on. And then we powered off the system. And in fact, that's the same day that we took the picture I showed you of the team making the DS1 and saying goodbye to it.
So there's no way that it can be reactivated. That was terminal, the operations that you had.
Well, okay, so I give wordy answers as it is. I didn't want to make this too wordy, but I will make it a little wordier. We did configure it so that if there were a need to try to reactivate it before it ran out of hydrazine, we could. And in fact, the way I even thought of it was, if this were a science fiction movie, what would happen would be we would deactivate it. We would discover Earth was at risk, from an impending asteroid impact or some other disaster, and only DS1 would be in position to save us. And indeed, so we turned it off in December of that year, 2001. The following March, somebody came up with an idea for it. Earth wasn't at risk of being wiped out, but we came up with another technology experiment to do. So we thought, we'll try to recontact it. However, we were not able to. And the reason we're confident is, by then, even though we had turned it off, it was still using the hydrazine to control its orientation so that its antenna would be pointed in the correct direction. So its solar wings would be pointed at the sun, so it would have electricity to operate its receiver, even though we had turned its transmitter off. But by then, undoubtedly, it had lost the hydrazine. So it couldn't even point its solar rays at the sun. Its computer would have been off. Its radio receiver would have been off. Without that, it would just tumble forever. So it now remains in orbit around the sun, just like Earth does. It's a permanent member of the solar system family. The way I always like to think of it is, it's an inert monument to human creativity and ingenuity, but there's no possibility of ever operating it again. Sorry for the wordy answer.
Nope, these are wonderful. We've got a question from Lindsay, who wants to know how fast ion propulsion can make the ship fly. And she puts in parentheses, well, her daughter wants to know. So this is probably a young person asking a very good question.
It is. So for Lindsay's daughter, and actually I tell you, old people like to know answers like this too. So how fast it can go well, again, I tend to give wordy answers, and I know we're running out of time. It depends in part on how much xenon propellant you carry. Once again, it's that action reaction. The more you carry, the faster you can go. There are limitations, however. Deep Space One changed its velocity by a little more than 10,000 miles per hour, which at the time was the fastest any spacecraft had ever achieved with its own propulsion system. You know, on Earth, we have rockets that send spacecraft out at much higher velocities, but I'm talking about the velocity after it had left the rocket. And of course, rockets use multiple stages and big fiery propulsion systems. This is what Deep Space One did just with its own propulsion system. Then Dawn, the mission that followed it with ion propulsion, exceeded DS1's record by a huge amount. Dawn got to about 25,000 miles per hour. So 2.5 times what Deep Space One did. And again, Deep Space One, as it was, set a record. It's probably possible to go even faster than that, but that's getting up to near the limit. It could be perhaps, optimistically, maybe 40,000 miles per hour. We're so low on time, I'll just say briefly, the more propellant you carry, the more propellant you have to push around. And pushing that propellant around is very costly. And probably, Lindsay, for your daughter, it's maybe a little too complicated for me to explain here. But eventually you reach that limit for that vague reason. I apologize if that wasn't satisfactory.
One question that I have, if I may, is
Sure.
the terms that you talked about that had a Star Trek connection, ion propulsion, of course, and impulse power. We know that in the world of astronomy, there is an actual union that formally classifies the names of craters and planetary bodies and so forth. Is there something similar where these terms that you have used are codified or basically, recorded as official in engineering terms, so it's not something that's just unique to your mission and to your preference?
So good question, but the short answer is no, there is not.
Darn.
So you're right about the IAU, the International Astronomical Union, but there are organizations that standardize terminology in many cases, but not in all areas. And so it was Deep Space One's, in fact, it was my personal choice to use impulse power, ion propulsion, but other projects are free to call things whatever they want. However, the way humankind works is you advance by building on others, right? And so Deep Space One and Dawn were NASA's only two interplanetary missions to use ion propulsion. So it was logical for Dawn, which, as it turns out, I happen to be in charge of also. But even if I hadn't been, they would call it ion propulsion as well, because they were building on what we invented, discovered, and did for Deep Space One. There's a lot more to ion propulsion than just the engine. It's a very, very complicated system, and learning how to operate it, how to fly a spacecraft with ion propulsion is very complicated. And we invented a lot of that on Deep Space One. So even though there was no official organization requiring Dawn to use that terminology, it was the logical terminology to use. And indeed, it was only logical. There you go. And so indeed, that's what they used.
Do we have time for one more, Dina, question, or are we doing okay?
One or two. We've got about 4 minutes.
Okay, there's one here from Mark that I want to relay. Mark wants to know, is it safe to say that ion propulsion greatly limits the mass, and in parentheses, no need for high amounts of fuel of the probe, making these deep exploration missions a realm of possibility?
I'm not sure I understood Mark's question. When you say greatly limits the mass,
I think, yeah, the second part I didn't quite understand on that as well, but perhaps maybe we could rephrase this as saying is perhaps, is ion propulsion, are there limiting factors in the size of the spacecraft that we could use ion propulsion with? Could we just tack on more ion propulsion units to make larger spacecraft, or is there a limit?
Okay, thank you for interpreting that question, because I had a different
take on it, but for the sake of expediency on time, I thought maybe we could do that.
So I had a different interpretation. So essentially what that's describing is stages, right? An ion propulsion stage where you would expend as much of that as you can, drop off that stage, and then have a smaller ion propulsion stage. Is that your interpretation,
I
Glenn?
think so. Yeah, run with it. Yeah.
Okay, you could do that, but it won't buy you that much because most of the mass of the ion propulsion system is still in the propellant. And so you still have to carry the propellant of that next ion propelled stage. So it is a good idea and it would help, but the amount, the quantitative benefit, I think would turn out to be pretty small. But you had advertised at the beginning that people could email questions. If we didn't interpret it correctly, I hope Mark will send an email and I'll give you the correct answer.
Right.
Or the full answer, I should say.
Okay, one more question. I think this will be the last one. Samantha asks a question. She says, so Voyager was referenced in Star Trek and you came full circle with Deep Space One. Why wasn't the Mars rover called R2D2?
Well, so that's a good question. The straightforward answer for why it wasn't called R2D2 is we, JPL and NASA, don't name our rovers. We still call it Mars 2020. We still call the previous one MSL, which stands for Mars Science Laboratory. We don't tend to call it Curiosity. But the names come from students. We conduct a contest around the country, invite students to not only propose names, but propose reasons for them and select them. I think it's a great education outreach activity. And we do sometimes internally use those names. But going back to Sojourner, Spirit, Opportunity, Curiosity, Perseverance, and the helicopter that's going to fly in a month or two, Ingenuity, those were all named by students. So if you know a student who wants to name the next one R2D2, by all means, enter the contest. I wouldn't be surprised if there were other entrants, other people entering that use the same names, but that's why.
Excellent. Well, with that, I think we'll wind down because we're 10-2 before our next session begins. Dr. Rayman, I want to thank you so very much for a wonderful session. I had many more questions to ask, but you're a very fascinating speaker. Thank you so much for joining us.
It was my pleasure. Thank you for inviting me. And thanks to all of you for